Okay, the last rate law we need to talk about is second order. And in second order, what we see is that when we double the concentration, the rate of the reaction actually quadruples. All right, so let's talk about the units for K if I have a reactant that's second order. So again, we know rate is equal to K times, again, we'll make my species generic and we'll say A, but this time it's going to be raised to the second power because it's a second order. We know rate has units of the change in concentration per unit time, and we'll just use seconds as our time. A is going to be the molarity squared. So we actually get moles squared per liter squared. All right, so let's see what we're going to have to do here so that I have the right units for my rate. All right, so I can actually only have 1 liter unit on for the rate. So this means that we're going to have a liters here so that these would actually reduce. And the same is true here, that I'm only going to be able to have mole. And so we are going to need this to reduce. So if I have a mole here, then this would reduce. And then we still need to account for those seconds. So there's my seconds. So K for second order would be liters per mole times seconds. Okay, let's look at the graph so we can derive our integrated rate law equation. So the graph we're actually looking at is the one here on the right. And so for this, it's 1 over the concentration. And again, we're just going to use A versus time. And time can be minutes and times can be seconds. So we're going to write our equation of the line. So Y is 1 over our concentration. Is equal to M. And notice this time my graph, the line increases over time. So it's going to be positive, and it's still, the slope is still K, our rate constant. X is our time in seconds. Okay. And B, our y-intercept would be 1 over the initial concentration. Okay, so we're going to use our integrated rate law equation to derive our half-life equation. So I'm going to rewrite my integrated rate law equation. All right, so if we're talking half-life, we're talking about taking half of the initial concentration. And I'm going to flip this around so that it doesn't look so wonky. So it would look like this. And again, T is going to be the half-life time. All right, so I'm going to move this 1 over the initial concentration to the other side. So we get 2 over the initial concentration minus 1 over the initial concentration is equal to K T 1/2. And so this is what I'm left with here. It's going to be 1 over the initial concentration equals K times T1 half. And we're going to want T1 half by itself, so we're going to divide both sides by K. So T1 half would be equal to 1 over the initial concentration times K. So this is our half-life equation. And again, you're not going to be expected to derive equations, but you're going to be expected to know them and be able to use them. Okay, so the next step then is that we're going to use our equations for zero order, first order, and second order to practice some problems.